right now we're having a podcast that will dive into signal processing and the science behind our digital life. We look forward to your presentation, Professor Hari.
Good afternoon, everyone. Thank you for the opportunity given to me for sharing some of the thoughts on signal processing, the science behind our digital life. I am representing the IEEE Signal Processing Society as the Vice President of Membership. I'm also a professor at the Indian Institute of Science, Bangalore. So let's explore what exactly is signal processing. I hope you can hear
What
this.
is signal processing? Signal processing is a branch of electrical engineering which pulls meaning from the broad sources of data that are all around us. But what does that mean exactly? It means signal processing is at the heart of our modern world. Signal processing powers modern communications,
How can I help you?
modern entertainment, and tomorrow's transportation. Signal processing is at the intersection of biotechnology, voice processing.
Access granted.
It's in our social interactions, learning to anticipate our needs and emotions, helping us hear the world around us and to better understand it.
سلام چطوری خوبی؟ Hi, how are you doing?
To bring new life and help us heal. Signal processing brings the world to our homes, adds clarity, and puts it in our pockets. Signal processing documents our cherished memories, helps to keep us safe, empowers the world of finance. Signal processing, processing the future.
Okay, so that gave you an idea about the signal processing, what it can do. Now let us look at what are signals and where do they exist. So we have signals everywhere. If you look at this plot or a chart, you can see a plot of a signal which is the ECG. When you go to a hospital, you can get an electrocardiogram. And you can see that this signal is the measurement of voltages along the time axis. So when your heart beats, there are electrical signals which are generated, and these are spikes which you see. As we speak, these signals are also picked up by the microphone and an electrical signal comes out. So if you record a statement like eat your raisins outdoors on the porch steps, the signal would look like this depending on your accent. So these are signals which we encounter every day and while we interact with our gadgets. The other kinds of signals are images which you are observing, and this is an image of a brain cross-section using magnetic resonance imaging. Now, using signal processing techniques, you can find out what is the structure of your brain tissue and understand how the brain functions. Now, we are all familiar with gadgets, and these gadgets have, your smartphones have what they call as accelerometers. So if you want to know how many steps you have taken, or how many kilometers you have walked or you have run, then you have signals which can be generated. In this plot, you will see that the signals which are being generated are from an accelerometer while you run, while you walk, and while you run. So the nature of the signal, depending on what your posture is, will change when you either walk or run. Now, these are very important signals for us to process. So how do we sense these signals, right? So all of us know that we need sensors to sense these signals. So we have microphones for speech and audio. So when we speak, the microphone converts the acoustic pressure on the diaphragm of the microphone and converts into an electrical signal. So when you sing, these microphones will generate electrical signals, which are then processed and actions are taken. Accelerometers. Accelerometers are devices which can sense the acceleration. Gyroscopes can also sense angular acceleration. So when you turn your smartphone upside by 90 degrees, you immediately know that your signal and the video will change. And that is because there is an accelerometer and a gyroscope which tells the system that you have rotated your smartphone by 90 degrees. Of course, cameras are there which will capture the two-dimensional images. The biomedical sensors, while like the ECG being recorded, will produce electrical signals which you can record and process. If you want to look at underwater acoustic signals, there are hydrophones. So hydrophones are sensors which can detect underwater acoustic signals. And these underwater acoustic signals can be used in systems like the sonar, or you want to understand if animals in the sea are communicating acoustically by producing acoustic signals. Geophones for seismic signals. The seismic signals are signals which are generated in term whenever there is an earthquake or there is an explosion. So geophones are sensors which can record these signals. So when you want to do signal processing, you first need to acquire these signals by building these sensors. Now, what is a signal processing system? Well, a signal processing system basically takes an input signal and processes and sends out an output signal. Like while I am speaking now, the microphone in my computer is converting my speech into electrical signals. It is digitizing, sending it over the internet in zeros and ones. And at your end, your system, your phone or your computer is receiving the signal in bits of zeros and ones. It aggregates all of them, converts it into an audio file, and the file is played back on your speaker, on your loudspeaker. And that's how the signal which where I'm speaking is you are able to hear and listen to me. Similarly, the camera in my computer is taking the picture or the slides, and then it is transmitting this two-dimensional signal. So in all this, whenever there is a signal, we do signal processing by transforming or doing something to the signal so that you can get the output signal. So what are the typical signal processing problems? Well, the problems can be classified as signal analysis. That is, you would like to know what are the various components of the signal. So imagine if I am speaking and there is a noise which is in my room, and you want to understand whether I am speaking and what is the noise due to. It could be a fan, it could be the air conditioner, or it could be, if you're in a house, a dog barking, it could be anything. So if you want to understand what is happening in the signal you receive, you may want to understand its various components, and that is called analysis. The next part is signal synthesis. That is the ability to reconstruct signals from available partial information. So suppose I have a signal and I have lost some data. While the internet is fluctuating in performance, some of the bits or some segment is not received. Is it possible for me to reconstruct the signal from partial information? So that is called synthesis, where you try to put together things to create a signal. The next one is signal discrimination, where you want to understand whether the signal belongs to a certain group. Suppose you receive a signal, you want to classify whether it is a female speaking or a male person speaking. Or if you receive a signal or which contains the sound of an elephant or the birds chirping, you want to understand what is this signal. Is it a bird? Is it an elephant? Is it a roar of a lion? Or is it a human being talking? And after that, you may want to classify if there are what kind of bird is chirping or tweeting. So that is called discrimination. That is, you want to separate these signals with certain characteristics. And then, of course, signal enhancement. We all have difficulty sometimes in understanding or listening to speech on a phone, on a mobile phone, when you are in traffic, because there are a lot of noise around you and you want to clean these noisy signals. You want to separate the noise out and you want to understand what is being said. So these are typical signal processing problems. So what do we need to do all this? Okay. If I need to do all those signal processing problems, we first want to understand, we build mathematical tools. Like in school, you are studying mathematics, physics, chemistry, biology. So we need to build some mathematical tools to represent signals, to transform them, and to interpret the output of the signal processing system. So in signal processing, when you want to build something, you first take the help of mathematics and you build mathematical tools, and the signal processing theory is built on that. For example, a transform is a Fourier transform is one such tool. This Fourier transform can represent a signal which you record as a function of time to be as in terms of frequencies. So you have the Fourier transform which will separate the signals in terms of the frequency content. I'll give you an example. So let's look at this plot. It is slightly maybe not clear, but the top two plots in the first row where you see time domain, if you look at the top left hand plot, you will see a signal as a function of time. And by looking at it, if I ask you, do you know how many sinusoids or how many tones are there in the signal, it will not be easy for you to tell me how many tones are there. But if you look at the bottom left plot, if I take the Fourier transform in the Fourier domain, you will see two sharp peaks of the signal. The same signal, what you saw on the top in time domain, is represented in the frequency domain by the plot in the bottom. Now this becomes very easy for you to decide that you know there are two tones or two frequencies which are in the signal above. Now you go to the right top plot. It is the same two sinusoids or two tones, but they have some noise added. When you have some noise added, you can see the difference between the right top plot and the left top plot, that it gets modified. So you will really not be able to determine how many tones or how many frequencies are there by just looking at the time domain signal. So if you want to know, you do the Fourier transform, and the bottom right plot will show you the same tones but with lot of noise also. So what this is telling you is a technique with a simple mathematical transformation called the Fourier transform. You can understand what is the signal or what are the frequency components in the signal. So this is a very simple example of trying to understand what is there when you receive a signal, to understand its components. And that is what the Fourier transform does. The Fourier transform is a very powerful mathematical signal processing tool which is used in many things, including your cell phones, or smartphones, and smart gadgets. So if I want to build a signal processing system, what exactly happens in a design of a signal processing system? So suppose I want to build a nice acoustic or a speech system. So first you need to define the problem. You have to say that this is what I want to do. So let's say I want to say that I want to find out what is the word or what are the words being spoken when somebody gives a lecture. So that is your problem specification, that you want to know what are the words in a sentence uttered by a speaker. So then you first understand and look at the theoretical solution by using all your mathematical tools available to you. And you say that, okay, I need to understand the signal. I need to find out what components it has. Then I need to understand what is being spoken. And then after what is being spoken, I have to identify the word, what has been spoken, and so on and so forth. So once you get a theoretical solution, you then implement it in software, on a computer. Like packages or software packages like MATLAB and others can be used, or you can write a program in C code. And you write a software code to test your theoretical equations, what you have built. And then once you see that it works, you then convert the code into an embedded system code where you put it on a Raspberry Pi or an Arduino or a complicated digital signal processing board. And once you do that, you then test the performance of the algorithm, whether it is meeting your problem specification. And in the problem specification, you need to specify what is the error you can tolerate, and so on and so forth. So this is what we do in signal processing. Okay? So I will play one more thing about signal processing in MRI.
Advancements in medical imaging allow us to study parts of the body, including the brain, like never before. But how are MRI images formed non-invasively and without radiation? The short answer? By relying on physics and signal processing, the science behind our digital lives. Magnetic resonance imaging, or MRI, leverages powerful magnetic fields, so powerful that they are at Magnetic resonance imaging, or MRI, leverages powerful magnetic fields, so powerful that they are at least 60,000 times stronger than the standard refrigerator magnet. This magnetic field targets hydrogen atom protons, making each proton align with or against the magnetic field. Then, repeated radio frequency current pulses at just the right frequency are introduced. When a pulse is turned on, it knocks the protons out of their alignment, changing the direction of their tiny magnetic fields. When the pulse is turned off, the protons gradually realign to their original state and each emits a tiny signal. As the radio frequency pulse is turned on and off repeatedly, millions of radio signals are generated from the combined output of the protons. The scanner directs magnetic gradients to different positions so that the data from the protons eventually fills a grid in what is called the K-space. Values in those locations represent the spatial frequency components of the MRI image. We apply a dominant signal processing algorithm known as the inverse of the fast Fourier transform on the K-space data to create the MRI image. The fast Fourier transform, or FFT, is one of the most versatile tools for scientists and engineers and identifies the frequencies in a signal. Another common application of the Fourier transform is JPEG image compression, which is used to reduce internet file sizes. But signal processing engineers are exploring ways to optimize the image construction process. Some MRIs take at least an hour or more to produce a perfect image. This has two negative effects: logistical strain on the healthcare facility, scanning a limited number of patients, and patient discomfort and claustrophobia. There is a need for a faster turnaround. To create images faster, certain frequency K-space data is often omitted or truncated, applying the inverse Fourier transform only on the remaining data. However, this results in aliasing artifacts, including the Gibbs phenomenon, which is a ringing that arises from truncating the K-space frequencies. Signal processing techniques to reduce these artifacts are being developed. Recently, another state-of-the-art signal processing technique is being investigated: compressed sensing. Compressed sensing uses sophisticated signal processing techniques to construct an image from partial K-space samples, resulting in faster image creation, but without the Gibbs ringing. These techniques are still evolving and are an area of opportunity for signal processing engineers to collaborate with doctors and technicians to disrupt the medical imaging industry. In fact, Facebook's Artificial Intelligence Research Group and the NYU School of Medicine have partnered to explore how artificial intelligence can use parallel imaging to generate scans faster. Engineers are also leveraging signal processing in new, innovative MRI techniques that study functions of the brain. As these techniques evolve, engineers can use these signal processing techniques to determine which parts of the brain are active when you tell a lie, develop wiring maps of neural connections in the brain, which will aid surgeons in brain tumor removals. Improve MR spectroscopy, another non-invasive test that measures biochemical changes in the brain, especially the presence of tumors. And advanced MRI diffusion imaging methods, which are used to study Alzheimer's, Parkinson's, and ADHD, and also predict who will benefit from a given therapy. Will you lead the next wave of signal processing that will transform the medical imaging industry? To learn more about these technologies, contact the IEEE Signal Processing Society Image, Video, and Multidimensional Signal Processing Technical Committee.
So signal processing challenges will remain as long as signals exist. So if you are interested in signal processing, you will always be busy. You will be kept busy because signals will always exist. I quickly want to tell who we are as an IEEE Signal Processing Society in a few minutes. IEEE is a world's largest professional network or an organization. And Signal Processing Society was established in 1948 and will be celebrating our 75th anniversary in 2023. It has more than 17,000 members from 120 countries, and we have a large network of chapters and student branch chapters. What we do, we publish a lot of research material in the form of magazines and research publications. We produce newsletters. We have a resource center where a lot of videos are available, and we also have blogs, and we create new journals. We organize a lot of events, conferences, and events all over the world, and a lot of members from all across the world do attend these meetings. Of course, during the pandemic, we have now shifted to virtual meetings. And a lot of activities are for students. We organize a signal processing cup, a video and image processing cup, and we also have a 5-minute video clip contest. So students can create innovative videos to explain a concept. And we also provide a lot of opportunities for jobs and provide conference discounts for students. And this is a volunteer organization. So a lot of work is done by volunteers like me, who are faculty members, who are students, who are industry professionals. But we also have a support of a staff which helps us. And the organization is spread across the world. And as you see that there are members in different parts of the world, which is, the structure is we have about 300 sections and about 220 chapters worldwide. And I understand that there is a signal processing chapter close to where you are in Zimbabwe and South Africa. And the chapter activities is to get together, you collaborate, you have technical talks, and you also have social events where you can relax and get to know each other. Thank you very much for providing us this opportunity to share about signal processing with you. And I'll be happy to answer any questions if there is time.
All right. Thank you so much, Mr. Hari, for such a profound and splendid presentation. I was really inspired and I learned a lot. So we're leaving this time to the audience for any questions. And then here's a question from Sharon Ramosi. What is the best way to start learning signal processing?
Oh, very good. There are a few sets of videos which you can do, or there are many textbooks. If you send me an email, I can send you a list of items which you can get. So let me, and I'm sharing my email in the chat box. I do not know if it is visible to others, or you could contact the organizers and then you can send me an email. I will give you more details. Okay. So this is a very good question. How can signal processing be applied in mathematics, physics, chemistry, and biology? So every field, as I told you, signal processing is mathematics in some sense. And if you want to understand and solve a physics problem, so let's assume that physics deals with physical things. As I told you, an accelerometer. If you want to use these transforms and to solve physics problems, you can do a lot of signal processing by measuring physics or building a physical system. So you want to build a nice smartphone to see how much you have run, it is physics. You need to look at it. Or you want to build devices. And in chemistry and biology also you can do, because you want to now understand how cells communicate with each other. Because everything has electrical signals associated with it. Ions have associations. You can measure how many ions in concentration. You want to classify cells. So all this is signal processing.
All right. Thank you so much, sir, for the clarification. On to the next question from Nyara Zomutiti. Which programming language do you usually use?
Yes, a good question. So first, when we do simulations, we use MATLAB, which is a software package. Then we use C programming.
Okay. Thank you so much, sir. On to the next question from the audience, from Bright Josam. How can signal processing be identified to be completed? Wow, that's a good question indeed.
Okay, I have. I do not understand what do you mean by completed. So when you, as I mentioned to you, when you define a problem, and your design of the algorithms achieves what you have set out to, then you can say you have completed that goal of achieving what you have set out to, and you measure them using performance metrics.
Okay, thank you so much, sir. Another question from Nyara Jomutiti. What advice would you like to give students who would like to pursue careers related to signal processing? Good
Okay, very good.
question.
Thank you. I think students should be good in mathematics. Students should understand programming so that you can build using Raspberry Pi or Arduino boards. And once you understand how, and also to understand how to take signals from the real natural world by working with sensors. So once you have a sensor with you, you should be able to connect it to your hardware platform. But all what you do should be based on good, sound mathematics, and mathematical foundation should be very strong so that you can write the correct program to make your systems work.
Wow, okay. Thank you so much. Here's another question from Caleb Mayer. What type of work does IEEE exactly do? Do you produce research report or do you work closely with hospitals to improve their signal processing systems or both?
Okay, so IEEE is basically a professional volunteer organization across the world. We have members who are professors, students, industry professionals. We are not a company, but we do research. And what happens is when a student or a researcher produces research, they need to share it with others. And for others to know whether we check, so we publish. So IEEE does a lot of publication of sharing of research work, and then interacts with industry to help build systems. So members from the industry also belong to IEEE. Members from academia, universities also belong to IEEE, and they can work together and create systems.
Yeah, that's very true. Thank you so much. On to the next question from Bayu Pratama. Is signal processing difficult? Okay.
I would I would say it is not difficult at all. And once you understand something, it will be very easy. It is very simple. Because it is very exciting. So even if it is difficult in the beginning, you will enjoy it.
Yeah, that's very true. That's very true. Um, any question from the audience? Okay, so I have a question for you. Do you offer any workshops enlightening people about signal processing? Any online workshops, any seminars that you do, provided there might be someone in the audience who's interested in participating as well in signal processing?
Yes, IEEE does conduct a lot of webinars. There are a lot of online videos also, which the society has created. I can share those links with the organizers, and they can then share it with all the participants.
Yeah.
I'll be able to provide more information if somebody is interested.
Okay. All right. Thank you so much, Mr. Gary. We really learned a lot. Signal processing is really a topic that we'd all want to learn about because very few people are knowledgeable about it. Thank you so much for the presentation.
Thank you very much for the opportunity. On all the best for your festival.
All right. Thank you so much. So for now, we are going to be taking a break. And please don't forget to go to the Africa Science Buskers Festival website to go and check out the parallel sessions there. Do not forget. And we've got a very big announcement to make for today. They say it is better to be late than never, isn't it? We are celebrating the birthday of a great icon as far as the science industry is concerned. It's the birthday of Paula Golden, who is the president of the Broadcom Foundation, which is the main organization which was sponsoring the 2020 Africa Science Baskers Festival. Thank you so much. Legends like Paula Gordon are worthy being celebrated, and we need to show that we are grateful for whatever they are doing for us. So for now, we are going to take a break. Don't forget to tune in for the next session of today. Have a great day. Bye.